I have said that I'm going to discuss the use of the right-hand rule in problems involving induction phenomena, and this is the video that we are going to do this discussion. Right? We would like to. There's a while loop in here. Let's just show it like that. This is a while loop, and we would like to find and compute the value of an EMF. So to be able to compute an EMF, we first have to express it along some direction. So as a result, we choose a direction and we then compute the EMF along that direction. All right, so this is then the EMF along that given direction. So notice that there is a choice involved in here. I could have chosen the direction in the opposite way. So that's also a possible choice. So as a result, the laws that we are going to express that involve the EMF somehow should respect that choice. So with different choices, I should be able to use the same laws. That also means that the EMF can, I should now accept that the fact that the EMF can be negative now. So that essentially means, for example, if the EMF in here is found as to be 10 volts, let's say positive 10 volts, in that case, somebody else who chose the direction in the opposite way and so therefore is using a different EMF along this chosen direction, in that case they are going to express the EMF with a different numerical value. So this time it is minus 10 volts. It's just like the current, right? So along this direction it is positive 10 volts. Along the opposite direction, this thing is the same thing as the negative 10 volts. So as a result, the EMF, we are going to accept that the EMF can be negative. And so as a result, we just choose a direction and stick with that direction and then compute the EMF along that direction. So this convention that the EMF can be negative is very useful because there are situations where, for example, there are these alternating current situations where the EMF actually changes direction. So we don't want to choose this reference frame continuously, periodically in these kind of problems. So this is one of the places where we accept the fact that the EMF can be a negative quantity. There are some situations where beforehand we don't know the direction of the EMF. So as a result, for this one, it is useful as well. In any case, so as a result, we choose a direction and then along this direction, we would like to compute the value of the EMF. The second thing is, of course, if you remember what we have written for the Faraday's law is the negative of the time derivative of the magnetic flux, and for the magnetic flux there is an area. So what we do in here is that there's in this wire loop we are imagining that there's an enclosed surface. It is shown by red in here. It is that surface in here. For that surface we are going to use an area vector, but for the case of area vector, we have said that there is a direction involved. So we just choose this direction. So in that case too, there's a choice involved. So I can choose that direction along that way because that's the only constraint on the area vector. It has to be perpendicular to the surface. So as long as it is perpendicular, I can choose this in two different ways. So that's one possibility. Right, let me erase. There is another possibility in here where the vector is like that and it's pointing like this, which can also be perpendicular to the surface. So there is also another choice involved in there. So depending on these two choices, right, the choice of the direction in which I measure the EMF and choice of the direction in which I express the area, the flux can change sign, the EMF can change sign, but we would like to choose them in a certain fixed way by convention so that I can express this relationship in the same way all the time. So when this happens, of course, I can use a definite sign in front. So the convention in here is to use the right-hand rule. So these two directions are chosen in the consistent with the right-hand rule. That means that if EMF's direction is like that, then the area vector should be chosen like this, right? With this choice, in that case, the Faraday's law with a negative sign is the correct one. There has to be a negative sign in there. Since we have used the similar kind of right-hand rules for different places, so as a result, we are going to stick with that right-hand rule. So the rules are always the same, but we won't forget the negative sign in front. Right, that's one way actually. I'm going to just look at some problems that I will actually illustrate how we can use that sign. But for now, let's just say something more about this right-hand rules. So let's then talk about this. So what happens if I choose the direction in the opposite way? So as a result, if I measure the EMF along that direction, so let me call this as E prime. In this case, I'm going to choose the area vector like that. So now it's pointing in this direction. Right. When I do this change, of course, flux changes sign, EMF changes sign, but this equation will still be valid. That's essentially what we are saying. So let me say a few more things about the right-hand rule. So we just keep seeing the right-hand rule in many different places. Since we started with the magnetic field concept, starting with the Biot-Savart law, of course, we have expressed the Biot-Savart law as a cross product. So therefore, in that cross product, of course, we have naturally the magnetic field. But without using the cross product concept, we can use the right-hand rule. We can use our right hand in many different ways to actually find the direction. I think I'm going to choose this white color. So, for example, the magnetic field produced by a wire. Let's just remember, if our thumb is in the direction of the current, in that case, 4 fingers show the direction of the magnetic field. Let's just remember that. Or in the case of a loop of wire, a circular loop of wire, in that case, the places change. Let me draw another right hand in here. Right, that's my right hand. If in that case the 4 fingers show the direction of the current, the thumb shows the direction of the magnetic field. So as a result, there are these 2 alternative ways of using the right hand, where the quantities just change their places. In any case, we have seen the Ampere's law. In the Ampere's law, we have also seen the right-hand rule in the same way, basically. But this time, of course, the loop was imagined. It was not physical. And the area was imagined. In our case, of course, the loop is a physical loop. It's a wire. But the enclosed area is imagined. But in any case, it doesn't matter. In that case, too, we just chose the direction on the loop and the area consistently, and in that case we have said that the Ampere's law is correct, with the correct sign, obviously. For defining the magnetic dipole moment, we have also used the same convention. In that case, the direction on the loop indicates a direction to measure the current, and again, this is the area that has to be chosen consistently with that direction, and the magnetic dipole moment is just the current times the area, and so somehow as a result of that we can consistently define the magnetic dipole moment. You see that there are many different places. Actually, when there is a magnetic field, you always use a right-hand rule. Why is that so? Let's just remember it quickly. Because we have defined the magnetic field through this magnetic force expression, and when we are discussing, of course, we have said that there are actually 2 vector quantities. One of them is a velocity, and so as a result, to obtain a 3rd vector quantity, we have to use a cross product. So somehow cross product involved in here, cross product of vectors. If you remember how we define the cross product of 2 vectors, let's say v and b, we have said that it has to be perpendicular to both of these vectors. And if you remember this discussion in the previous semester, it's just a mathematics basically, but it's an important discussion. A vector that has this property of being perpendicular to 2 given directions, there are 2 possible solutions for that, and somehow we had to use use some kind of a convention to choose the correct direction. So we then define the cross product with our right-hand rule, right? We have specified the direction uniquely in that way. But we could have chosen the other direction. So that would be basically a left-hand rule. So we can imagine something like this. Perhaps in another star, around another star, there's a planet and there are these creatures who are doing physics as well. I'm going to call these as Borgs. Borgs might also be discussing physics like that in the way that we are discussing, but perhaps they are using their left hands to describe the left-hand rule to describe the cross product. So as a result, they are still going to use the same magnetic force expression, but since they are using their left hands, their magnetic fields will be opposite to our magnetic field. So in our case, for example, the magnetic field on Earth is pointing towards north. If Borgs came to Earth, they would say that their magnetic fields is actually pointing south, right? They are going to describe it like that. In any case, it's just a definition. It's a mathematical definition. This depends on how you define the cross product. So as a result, they describe the same physical field, the same physical entity, magnetic field, by using a different mathematical vector. That's all. But physically, they should be able to describe the same physics. But since there are these two possible ways of using the cross product, we always use the right hands consistently. We always use our right hands consistently. But I mean, there might be this other way as well. But in any case, whenever we relate the magnetic field to a physical quantity, therefore, somehow I have to invoke the right-hand rule. So that's why we are seeing all the right-hand rules in here. So the next question in here is that, can I find the direction of the EMF without using my right hand? No, you cannot do that, because that's essentially is a problem with the definition of the direction of the magnetic field. So somehow, at the point when we define the magnetic force concept, we have made a choice in there, and somehow we have to remember that choice. So as a result, we have to use the right-hand rule all the time. But perhaps by using a different kind of a right-hand rule, like this one, for example, I mean, if you know how to compute the magnetic field direction for a current-carrying loop, let's say, in that case, by using the right-hand rule that you have used in here, you can perhaps compute the direction in a slightly different way, right? That's essentially what we call as Lenz law, right? But I'll just try to describe it. So essentially, the problem is like that. There's a current wire in here. Of course, we have just a single wire. There's a current in there, and then you know how to find the direction of the magnetic field produced, at least at points, I don't know, on the inside of the this current loop. I don't know, you just have to think about this enclosed surface and some point on that surface perhaps. You know how to use your right hand to compute that direction. So if you're comfortable with this, then you can easily use the Lenz law. So that basically describes it like that. So let me erase this picture, because this is kind of complicated. A lot of people get confused about this. Right. I'm going to choose a wire loop in here. So that's a wire. There's some certain magnetic field in here. I'm going to call that magnetic field as the external magnetic field. Right. It is possible that that external magnetic field is changing, or this wire is moving, whatever. I don't know what it is, but the flux due to that external magnetic field is changing. Right? This changes with time, of course. When I say changes, of course, it changes with time. Right? So let's remember that when the flux changes, Faraday's law basically tells us that there's an induced EMF in here. So I'm going to call this as E-induced so that we are clear about what we are talking about. Perhaps there might be some other EMF device on the wire loop. Perhaps there's a battery. I don't know. But we are not talking about this. We are talking about the induced EMF produced by the change in the flux due to that external magnetic field. All right. So depending on the resistance on the wire, there will be an induced current in here. But whatever the resistance is, of course, we know that this induced current would be in the same direction as this induced EMF. So that means along that direction, if the EMF is positive, then the current is also positive. All right. There's another thing. So this induced EMF, just imagine that this might produce a magnetic field. So that magnetic field would be different than the magnetic field, the original magnetic field that produced everything, right? So there's an induced magnetic field in here. There's a secondary magnetic field. So that's the induced one. So let me raise this one in here, right? So there's an additional magnetic field. And then this induced magnetic field then produces a flux. So there's an induced magnetic field. So this this produces a flux through the same area. Now, what Lenz law says is that everything started by this flux change of this original flux produced by the external magnetic field. And at the end, because of these chain of physical influences, there's a new flux produced. So this induced flux somehow opposes the change that actually started everything. Right? This is just in an opposite direction. Some people try to understand this as prevents the flux change. No, it doesn't prevent. That's not possible. This is just a convention to find the direction of the induced EMF and induced current. Actually, the induced EMF. It's just a convention to find the direction. It doesn't say anything about the magnitude. So we are not claiming that this induced flux somehow overcomes this flux change, so therefore the flux doesn't change or anything like that. We don't claim anything like this. Flux always changes, but at least this is opposite to that. So as a result, this is how we use the Lenz law. So we just express it like that. So if there's a situation where the flux changes, so therefore there's an induced EMF, then the direction of the induced EMF is in such a way that the resultant induced flux would try to oppose the change that have produced it, essentially, or something like that. So the best way is to express this is to actually discuss it. So I'm going to discuss it within that problem. So I'm going to use these two approaches. One of them is this, right? It's the EMF is equal to minus d phi over dt. How we can use this minus sign? So that's the first question. The second one is, well, we don't want to use the minus sign, so I'm going to use this equation to find the magnitude of the EMF only, but I'm going to use Lenz law to find the direction. So there are these two possibilities, but let me start with the minus sign. So in here, of course, to be able to use the minus sign, I have to choose the directions consistently, right? Let me again describe the picture in here first before starting these directions. There's a magnetic field in here. This is out of the screen. There's no magnetic field in here, so therefore this is kind of a non-uniform magnetic field. I just have some kind of a rectangular wire frame and I'm pulling it out. I'm going to discuss this problem later. But here I'm just going to discuss the directions only. What's the direction of the induced EMF in here, right? So to be able to find this, I just choose a direction. Doesn't matter what it is. And I would like to find the EMF along that direction. But for now, I would like to understand whether this EMF is negative or positive, right? So I chose a direction. So by convention, therefore, I have an enclosed surface in here. It is that enclosed surface. This is rectangular in shape, so I'm going to choose it as flat. So there's an area vector along on that surface. So that area vector would be positive. Right? It is pointing, I'm sorry, area vector would be pointing towards us. I shouldn't have said positive. So area vector is pointing towards us. And so as a result, I have to use this area vector to compute the flux. So you can see that the flux is, well, in that case, it's the magnetic field dotted with the area. Let me just write it down like that, right? So this is essentially the dot product of the magnetic field with the area of the part of the surface where there is magnetic field, right? It's just that area. But in any case, since these two vectors are parallel to each other, so this is positive, right? But of course, flux is a positive quantity, but it is changing because somebody is pulling this wire frame out. So how is it changing? Well, the magnitude of the area is decreasing, so therefore flux is decreasing. So that means flux as a quantity decreases with time. It actually decreases linearly, but it's not that important. So you have to realize that it is decreasing. That's the important point. So then, therefore, we use this law. So the EMF is equal to minus the rate of change of the flux. So flux is decreasing, so therefore its rate of change is negative. So therefore EMF is positive. So that means along that direction that we have chosen, the EMF is positive. All right, so that's the answer to the question of what's the direction of the EMF. So therefore, in that case, the current would be flowing in the counterclockwise direction. But I'm going to solve the same problem again, this time with a different choice. All right, I'm going to start from the beginning. Sorry about this, but I need to somehow convince you that this doesn't depend on the choices in here. So as a result, I'm going to choose this direction on the wire loop, and I would like to find the value of the EMF, but here I just want to find the sign of the EMF. Okay, so by the right-hand rule, therefore, I need to choose the area vector to be pointing into the screen. Area vector is now pointing into the screen, which means in that case, flux is same expression again. It's the B dot dA, but of course, since the magnetic field is uniform, this is the dot product of the magnetic field with this area of that part again. So it's the same story, but this time we have the product of two anti-parallel vectors. So therefore, their dot product is negative. Okay, so I just use this thing to find the sign of the flux, basically. Now, but of course, I'm pulling the frame out, so therefore this flux is changing. How does it change? Well, it becomes closer to zero, so therefore it is increasing, right? So phi is increasing. Why? Because I can plot this flux versus time graph. So at the time shown, of course, the flux is negative, it is here. But of course, eventually when I'm moving this frame out, of course, it will just completely come out of the magnetic field at some point, so it will become zero. So therefore, the flux is increasing in here. So that means the rate of change of the flux is positive. Flux is negative, but its rate of change is positive. So therefore, by Faraday's law, right, it's the negative of the rate of change of the flux. EMF is equal to minus of some positive quantity, so therefore EMF is negative. Which means, right, let's remember our direction of choice in here. I have chosen the direction in the clockwise direction, so the value of the EMF in the clockwise direction is negative. Right, that's what we found. So let me then write it down like this. So this EMF is a negative something. As I said, I'm going to compute what that thing is. So that's basically the answer to the question. So you don't have to change the direction in here and re-express the EMF. But if you want to change it, so as a result, if you want to express it along that direction, so and therefore in the counterclockwise direction, the EMF would be positive. All right, so that's the second alternative way. So again, this uses the negative sign in Faraday's law. All right, so let me erase again everything in here. This time I'm not going to use any sign convention. Well, sometimes, of course, this is kind of easier to use a direction for area and things like that, because this is kind of easier to discuss. So I'm somehow more comfortable with the Faraday's law with a minus sign than with the Lenz law. In any case, so this is moving out. So you can see that in here, of course, the flux is the fundamental quantity. So it is that area. Let me use this red color to show this area in here with a thick font. So it is that area in here where the magnetic field is changing. So that area is decreasing. So therefore the magnetic flux is decreasing in magnitude. Right? I said that I'm not going to choose a direction, but I think I cannot do this. So let's choose a direction for the area in the outward direction. So flux would be positive in that case. Doesn't matter what it is, but probably that's the best way. So in the outward direction, therefore, out of the screen direction, the flux is positive, but it is decreasing. Right? It is decreasing. So somehow, therefore, an induced I don't know how to do this. All right. So an induced current, let me just say it like that. So there's some kind of an induced current. First, there is an induced EMF, and therefore there's an induced current that's produced in here. I don't know its magnitude. Perhaps it's very small because there's a very large resistance in here. Perhaps this is almost an insulator, so therefore this current is very small. So therefore the magnetic field produced by this thing is negligible, but I don't care how small it is. I'm just interested in its direction. So I know that the flux changes like that is this flux in here in the outward direction is decreasing. This induced current should be in such a direction such that right, I'm going to use this color. So the magnetic field produced by the induced current should be in the out of the page direction, because the induced current opposes that change. What was the change? Well, because the flux was increasing. So this induced current would try to increase the flux back again, right? Flux is decreasing, that causes an induction, but the induced magnetic field somehow opposes that change. So therefore it has to be in the out of the page direction, which then tells us that the induced current must be in this direction, which is therefore the same as the induced EMF. All right, that's essentially how we find the direction by using Lenz law. As a result, somehow you have to understand how the flux changes and how a magnetic field produced within the loop opposes that change. And so by using that, you can understand what's going on. So I think I have another example in here. So this time the magnetic field is into the screen, and this time I'm moving the wireframe into the magnetic field. I don't know what the direction is, but let's go ahead and let's start with the Lenz law in here. So in that case, again, there's a change in the area. So this area is basically increasing. So since the magnetic field is into the screen, in that case, this might be reasonable to choose the area vector to be into the screen too. So in that case, flux with that convention is increasing. right? The flux is increasing, so therefore the induced current would produce an induced magnetic field which opposes that change. So that means it would produce a induced magnetic field like that in the out of the board direction. So this be induced. In any case, so that would be the direction of the induced magnetic field. So that would then imply that the induced current is also counterclockwise in here. All right, that's basically by using Lenz law. Let me erase these, or let me undo. Now I'm going to erase these. Right. Let's then talk about the situation with with the sign. So I choose a direction on the while loop to express the EMF. That's first direction. So therefore, by right-hand rule, I am going to choose my area vector to be pointing out of the screen, which means flux is negative now, but it is negative though its magnitude is increasing. So that means flux versus time graph is like that. This is flux. It is negative, but its magnitude is increasing. So that means in absolute value it is increasing. So that means phi is decreasing. So d phi over dt is a negative quantity now. So therefore the EMF is equal to the negative of the rate of change of the flux is therefore is a positive quantity. So therefore the EMF is positive along that chosen direction. I don't want to solve the same problem by the choice of the other direction. I'm just going to leave it to you. So as a result, I think these two exercises would be enough. In either case, of course, what is important is that which one of them is you are comfortable with. I'm actually comfortable with this thing in here, so where the direction of the area and the EMF direction, they are chosen consistently. But if you are comfortable with the Lenz law, that's also okay.